back to part 5 of thermal physics. Now we're going to start off with properties of matter. Let's start with diffusion. Diffusion is the movement of particles from an area of high concentration to an area of low concentration. Give an example of this. Anybody? Any takers? Okay, so an example of this would be just like the picture suggests in the right hand corner, perfume, and another example would be cooking. And so what happens in this situation, you have a high concentration of whatever substance is being diffused in one area, and then this high concentration is now being sent out, or is now moving out to an area where it didn't exist before, so it's at a lower concentration on the outside. Now, here's some variables that contribute to diffusion. The speed of diffusion of a gas depends on the speed of its molecules and the mass of its molecules. So in other words, the lighter the molecule, the faster it will travel. So here I have a little drawing showing you exactly what I'm trying to explain. And in this drawing you have two gases that was, well, two liquids or fluids that were soaked in cotton balls, and eventually they're going to start dissipate. They're going to become gases, and so these gases are going to move along this glass tube. So this is a glass tube right here, and some type of product is going to be made. However, the product is not made at the center of the glass tube. The product is made closer to HCl than to NH3. Now HCl represents hydrochloric acid. Right? And NH3 represents ammonia. And they are both gases in these states right here. They become gases after this. They're volatile, so they become gases eventually. And what I did is worked out the mass of the molecule itself. And if you look at it, you'll see that hydrogen is 1 gram. If you do chemistry, you'd know this. And chlorine is 35. An atom of chlorine is 35.5 grams. So an atom of hydrogen is 1 gram. An atom of chlorine is 35.5 grams. You add that together, you get 36.5 grams. An atom of nitrogen is 14 grams, where an atom of hydrogen is 1 gram. However, this 3 indicates that there are 3 atoms of hydrogen involved in the bonding of ammonia. And so when you add these two together, you get 17 grams. From the looks of it, you'd realize that one gas is definitely heavier than the other, and that gas which is heavier is hydrochloric acid, and so it's going to travel more slowly than the ammonia, and that is why ammonia was able to travel closer to hydrochloric acid to form this compound known as ammonium chloride. Okay, now surface tension. So remember what we are doing today. We are learning about properties of matter, so their behavior in nature. So now we're going to be, first we investigated diffusion. So the behavior of molecules or particles that are diffusing is such that the particles move from a higher concentration to a lower concentration. And here again, we're going to talk about some behavior and the behavior of water particles now. So whenever you hear the word surface tension, you refer to water particles. The surface of a liquid behaves as if it were covered with an elastic scale that is strained to shrink. This effect is called surface tension. How can surface tension be reduced? Well, we'll investigate this in a while. Now, surface tension is due to the molecules in a liquid surface being slightly farther apart than normal, like those in a stretched wire. So in the case of water, where surface tension is exhibited every single day, we have something called bonding. The surface tension is due to hydrogen bonding. Now here I have a drawing of a water molecule. You have the oxygen atom right here and the two hydrogen atoms. Remember, water is, the molecular form for water is H2O. So I have the two hydrogen atoms and the one oxygen atom. Okay, these two bunny ears up here indicate the lone pairs that exist on the oxygen atom. If you don't do chemistry, you might not be able to relate, but it's worth the listen. Now, inside of the fluid of water, you have many molecules. Okay, and these lone pairs are highly electronegative. And if you look at it this way, I'm going to tell you right now that water is regarded as a very polar molecule. And it's polar because of the differences, the wide differences of electronegativity between the hydrogen atom and the oxygen atom. Now, the hydrogen atom has an electronegativity of about 2, while oxygen has an electronegativity of about 3.5. Because of this large difference between the two, you're going to have a polar on electron density towards the oxygen, right? And so because of this high electron density right here, this electron density is going to be attracted to hydrogen atoms that are bonded to other oxygens, right? So basically the molecules are attracted to, the water molecules are attracted to other molecules within the fluid. So let me draw that out right here. So in this case, you have hydrogen and another oxygen being attracted to that hydrogen. A lone pair on that oxygen is attracted to that hydrogen. And it goes on and on and on, on and on. So let me draw another one. Another one, and you see the attraction there for that, right? And if I draw more, you're going to see there's an attraction between each lone pair of the oxygen atom, and so this is referred to as hydrogen bonding. So that's the hydrogen bonding. It's intermolecular. So intermolecular means in between molecules. Intra means in between atoms. So this is in between molecules. So you would consider this an entire molecule right here, right? This is called hydrogen bonding, which exists between the molecules. So this is intermolecular. Alright, so I hope that you understand that. Now, adhesion and cohesion. Now, when it comes to fluids, the way they behave is based on the ability to adhere and cohere to things, right? So the force of attraction between molecules of the same substance is known as cohesion. So this exists within the fluid itself, right? And the force of attraction between molecules of different substances is known as adhesion. So that is between a substance and another substance. Like for instance, for cohesion, you would talk about the hydrogen bonding inside of the water, right, between other water molecules. And with adhesion, you would talk about water adhering to something like glass or wood or even your skin. Okay, now I have a picture here of water and mercury. If you look at it, you would see that they behave differently when they're inside of a test tube. For instance, both have meniscus, right? They have meniscus, and water's meniscus is like a happy face. It's happy, whereas mercury's meniscus is a frown. This indicates that water has a higher adhesion factor to the glass, whereas mercury has a higher cohesion factor because mercury prefers to be with itself. For instance, if you throw water out of this test tube right now, this water would just eventually spread across any surface, right? It would spread across and probably drip off of the surface, but it would definitely spread across that surface. However, when it comes to mercury, if you were to spill that mercury or pour that mercury out on a tabletop, it would make beads. So the beads would actually just roll off of the table. Okay? So that is what we mean by that. The adhesion of water to glass is greater than the cohesion of water molecules with itself. This is why water is able to wet and clean glass by spreading a thin film upon it. In contrast, mercury on glass forms small spherical drops or large flattened ones if applied to glass. Why is this so? And again, remember, mercury likes to hang with itself. It's like an introvert. So you could say that mercury is like an introvert, and so it prefers to form beads. It prefers to bead up whenever it falls on any surface. That's how come if you break a thermometer and the mercury comes out, you realize that it's very hard to clean up because the mercury is going to form very small beads that literally just roll off the table. Okay? While water, on the other hand, if it falls on a table, when water spills on a table, it flattens out. It flattens out and it doesn't roll away. More so, it drips off. You know, it's easier to clean up. So it has a higher adhesion fact. It adheres to the table after a while. Give it time, right? However, with mercury, it's not going to soak into the table. Mercury is just going to make sure it balls up and coheres to itself, right? It's going to find some cohesion amongst its partners, and it's going to prefer to be by itself. So think of water as the extrovert and the mercury as the introvert, right? So it makes sense because remember, water is a universal solvent. It likes to mix and match with many different things that are just like itself. Like once something is polar, it will mix in water, right? And here is a picture of what I was talking about. So water is polar, and so basically I'm just going to explain why things either mix with water or why they don't mix with water. In this case, we have water which is polar. Hydrogen is highly electropositive, whereas oxygen is highly electronegative, right? And so water wants to mix with things that are also polar. This is why water does not mix with oil, because oil is non-polar. Why is it non-polar? Because the electronegativity between carbon and hydrogen is very close, right? Um, Hydrogen's electronegativity again is about 2 or 2.2, something like that. I think it's 2.2. And En stands for electronegativity. So I'm going to put En, and I'm going to say electronegativity. So let me move it over a little bit. So En is equal to electronegativity. So basically how negative something is. So in this case, hydrogen is 2.2, carbon is 2.5. So that's nice because the degrees of separation here is about 0.3. So it's very close. Anything beyond 0.6, the indifference between electronegativities would cause a pull on electron density. So the electron density here would pull towards the oxygen. Now this, because the difference in electronegativities is so small or minor, this molecule will be termed as nonpolar. Okay, so that is why when you mix oil and water, oil does not mix well with water. It sits on top of water because it's less dense than water. Okay, now how does water clean? Basically water doesn't really clean it. Water more so wet stuff, but it doesn't clean. So to get water to clean, it needs a catalyst. It needs something to help it to clean, and that is something called a detergent. Now detergents are made up of many what do you want to call this, like molecules that have hydrophilic heads and hydrophobic tails, right? And so the hydrophilic head is the one that would interact with the water, while the hydrophobic tail is the part that would interact with the grease or the dirt, right? And so we say hydrophilic head licks water, to remember that, and hydrophobic tail has a phobia to water. Now this detergent, when you add it to water and you add this soapy water solution to dirt, the detergent along with the water, detergent mixes well. The hydrophilic head of the detergent mixes well with the water, so it interacts with the water, while the hydrophobic tail interacts with the dirt because the hydrophobic tail is actually non-polar. And what happens is that the detergent forms something called a micelle around the dirt, and this micelle is able to be lifted up off of soiled clothing and whisked away into the water. That is why after a while when you add detergent, it becomes brown or dark colored, because the detergent is doing its job, right? So that is how water and detergents work to remove dirt. The cleaning action of detergents depends on their ability to weaken the cohesion of water molecules. Again, the cleaning action of detergents depends on the ability to weaken the cohesion factor or the cohesion of water molecules amongst themselves. Instead of forming drops on greasy clothes, detergents make it easier for water to penetrate the fabric to release the dirt. And that was the explanation I gave a while ago. How does water move along a capillary tube and why? Well, we're going to explore that in a while. So the action of blotting paper is due to capillary rise in the narrow spaces between the fibers it contains. Mercury is depressed in a capillary tube. Why? Now we're going to remember, water has what? Water has water coheres to itself well. And it also adheres to other materials well. So because of these two factors, if water is going up through something like a straw or capillary tube, it moves along because it's able to keep itself together as well as adhere to the walls of the capillary tube. So it's a dual effort. So it coheres to itself, all the molecules cohere to themselves, and they're also, in sticking together, they're also able to stick to the walls of the capillary tube, thereby moving upwards depending on the pressure on the inside of the capillary tube. That's a whole other story, but it will move upwards. Now when it comes to mercury, remember that mercury coheres to itself well, very well. But, and a big but, it doesn't like to adhere to stuff at all. At all. It's like, leave me alone. That's what mercury is like. It's like, leave me alone. So mercury prefers to bead up. Just bead up. And that's why when it's in a capillary tube, it will go in, but guess what? It's not as, it doesn't move along the capillary tube as easily as water would. Alright? So there must be some sort of driving force to cause mercury to move up a capillary tube, because guess what? Mercury is actually often put into a capillary tube inside of thermometers, right? And so the driving force that causes mercury to move up a capillary tube is heat, right? Heat will cause that mercury to expand and move along the capillary tube, right? I was gonna draw something on that. So alright, so again, looking at properties of materials, mechanical properties of materials. When selecting a material for a particular job, we need to know how it behaves when forces act on it. Hence, we need to know that a material's mechanical properties, what a material's mechanical properties are. We need to know what a material's mechanical properties are. So here are some properties. There are 5 of them. We need to know the strength. The strength of some materials depends on how the force is applied. We need to know the stiffness of that material. A stiff material resists forces which try to change its shape or size or both. Elasticity. An elastic material such as rubber recovers its original shape and size after the force deforming it has been removed. Ductility. Materials which can be rolled into sheets drawn into wires, are worked into other useful shapes without breaking are ductile. Brittleness. A brittle material is fragile and breaks suddenly. So we need to know all of these properties of metals before we use them. Understood? Stretching a wire. Now, stretching a wire, we do this often to prove Hooke's law, where wires are used as springs, and we want to determine, most times, we want to determine maybe the elastic limit sometimes, so that means we want to stretch the spring out, or we just want to see how the extension of a spring varies with the load being added to it. And then from there, we usually want to calculate the spring constant of the spring. Right? So, useful information about mechanical properties is obtained from stretching a long wire of material by gradually loading it with a weight. The graph obtained by plotting extension against load is similar to that of stretching a spring. At the elastic limit, molecules are pulled slightly farther apart. The deformation is elastic, and the wire recovers its original length when the load is removed. When you pass the elastic limit now, the atoms are actually slipping over each other, and the deformation is referred to as plastic. And if you unload it, it will never return to its original length. Alright, so let's try to answer these questions. Explain why diffusion occurs more quickly in a gas than in a liquid. Well, intermolecular bonds for one. There are intermolecular bonds between molecules in a liquid as opposed to a gas. So because gas molecules will be more freer than molecules in a liquid, diffusion will occur faster. Now diffusion is still quite slow even in a gas. That's because some gases have a lot of mass, right? So because that's a factor in the speed or rate of diffusion, you will have that gas traveling slowly if it's very heavy. An inflated balloon gradually goes down even when tied. Well, remember gases, well, a knot is not perfect. There are spaces between knots, and so what would happen is that the gas would find these spaces, these cracks, and they would find themselves passing through these spaces, and eventually the balloon will go down. Explain the following observations as fully as you can. A small needle may be floated on the surface of water, but if a drop of detergent is added to the water, the needle sinks. Right, and so insects can stand. So one, what is happening? That goes right back to cohesion. The detergent is disrupting the cohesion, the cohesiveness between the molecules, which is basically the hydrogen bonding. This is disrupting the hydrogen bondings, and so once that disruption has been put in place, the needle will no longer have the ability to float on the surface area, because remember the needle was floating due to the hydrogen bonds. Explain the following observation. Why can insects stand on the surface of a pond? And they can stand on the surface of a pond because of hydrogen bonding. The hydrogen bonding has not been disrupted, and the insect themselves are very light, so they themselves don't disrupt the hydrogen bonding that's existing in water. State two practical uses of capillary action. Well, we mentioned it. A thermometer uses capillary action. Plants, water traveling up to the xylem of plants is due to capillary action. Blotting, using blotting paper, the water travels along the fibers of the blotting paper, which is also an example of capillary action. Using towels to clean up messes, example of capillary action. So many examples. Alright, so this is the end of part 5 of thermal physics, and we're going to be moving on to part 6, and that will bring us to specific heat capacity. See you around.